This is Benjamin Bacon, owner of Plain Space Design, and I'm about to explain a solution to a problem that I encountered while working on my design for this inertial propulsion system. And the problem was that I could not find a standard reference design for variable mass systems such as this. But here, I think that I have one that is satisfactory, and so I'm going to describe it to you here. First, let's go through the mechanical system. As a review, M1 and M2 and M3 are the masses. M3 is a fluid mass, and you see it's a square that intersects both because it has the ability to associate itself with M1 or M2. It's a fluid mass that can flow between either one and associate itself rigidly with either mass. And we have a reciprocating force that can pull these masses together or force them apart. And here there is a diagram that shows the waveforms in the time domain. And we notice that we start out with M2 and M3 connected. So M3 is associated with M2. And we have a positive force. And this positive force will cause the masses to try to move away from each other, apart. And since M1 is much lighter than M2 and M3 combined, it will have a higher acceleration in this direction, while M2 and M3 will have a lower acceleration in that direction. And then we turn the force off at this point, and then we flow the mass. So M3 flows off of M2 and on to M1. So now we have M1 plus M3 forward here, and at this point the force is reversed in polarity and tries to pull the masses together. And then because of that, we have an acceleration of M2 in the direction of flight that is much higher than the combination of M plus M3 trying to go in the other direction. So at the end of the cycle, we're trying to have a net motion in the direction of flight. And by repeating this cycle over and over again, we try to get to the point where we have achieved unilateral translation in the flight direction. However, when you're trying to build your simulator, you will find that if you don't model it correctly, you will get results such as it will fly this direction, and then after like several cycles, it will start to go backwards and come back to where it began. Sometimes you will have simulations, if your model is not correct, where the two masses begin to stray away from each other, and this gap between them becomes larger and larger, diverges, or sometimes they converge, and you have collisions and all kinds of events going on that you do not want to happen in the design. So that is why it's important to be able to get a very good model. So we have here an analog with an electrical circuit. This is a mobility analog where current represents force, capacitances represents masses, and of course we will have the voltage to have the same role as the velocity. The acceleration is the derivative of the voltage with respect to time, so this equation is equivalent to force equals mass times acceleration that we have in the mechanical system. So now we will notice that to make this an analog to mass flow, I used a component called a differential variable capacitor. And the way this differential variable capacitor works is that when you rotate the knob on the capacitor, one capacitance goes down or decreases and the other increases, so they go in opposite directions. This is the same as moving a mass from here to there or from there to there just by rotating the axis of the device. And this is an actual device that you could purchase at a store or build yourself. So let's look at how this analog is the same as this mechanical model. If we were to do the same sequence, we would have from the waveforms C4 would be at its maximum capacities. These two capacitances being in parallel will be an addition of the masses, the fluid mass added to the mass of the M2. Then we apply a positive current, which is equivalent to a positive force, and that would tell us what would happen if these two modules were moving apart. We would get an acceleration on this one, a rate of change of voltage that is much higher than the rate of change of voltage over here, because this is a mutual force. So this would go positive voltage this way, negative voltage that way. Or rate of change of voltage would be negative, going down. Now, the current is turned off, and we simulate the mass flow by turning the shaft on the differential variable capacitor, so that now the capacitance is over here, maximum, and zero capacitance on this one. So now we have the inertia analog on this block. And then we turn the current on in the opposite direction, that is equivalent to reversing the force. And now acceleration on this one, the voltage tries to go down or descends, while the voltage on this one goes up, but it will be higher here because this has a smaller capacitance and a higher voltage, which is the analog of having a higher acceleration on M2. So we have created a analog that is correct, but that is not the end of it. We can go deeper, and if this analog is correct in other areas, then it would be far more useful. For instance, we notice that we turn the current off, and then the mass flows between the two blocks. Well, what if we could find out what would happen as that mass flow occurs? Is this also an equivalent analog to the mechanical system when we are rotating that shaft on the differential variable capacitor? And then even deeper, what would happen if we have the forces on at the same time as the mass flows? So if this circuit is an equivalent even on that level, then it can be a quick way to estimate what would happen and not have to include all of the computational fluid dynamics that you would have to get into to find out what occurs in the mechanical model. But we could quickly estimate using this electrical analog. And that is the utility of having it, but we do not know yet that it is accurate on that level, only that it sequentially models this mechanical system accurately. And for the other questions, we would have to set up a circuit in a simulator, and also still have to understand what happens in the mechanical model to find out whether this is accurate on all levels of analysis.